Hi there, in this video we're going to go over an example of the complex version of the Fourier series. So let's say we want to approximate a function. It's a square wave and it's centered on the origin and it's got a period of say t0. So from there to there is the period t0. Okay, and this is the time axis and that's a real number line. Now the Fourier series tells us that we want to approximate a function f of t given a series of sinusoidal functions. Okay, but we've put it in complex form, so it's actually in the form of the e to the I omega. Okay, so we're going to have a magnitude and e to the I in omega naught t. Now we can find the values of Cn using our dot product, and our dot product can be written as 1 upon t0, the integral from 0 to t0 of our function f of t times the basis. The basis is e to the minus I in omega naught t by dt. Okay, so we derived that in the previous video. So what I want to do is find these values of Cn. Okay, so if I just, we can write that again as Cn equals 1 upon t naught, the integral. Now we can just replace the summation limits because there's nothing happens in this point here between the 0 and t naught. So what we can do is we can replace it by the limits here, so we can give that little distance there a value of tau. So this point here will be minus tau upon 2, and this point here will be tau upon 2. Okay, so the limits of that integration are minus tau upon 2 to tau upon 2 of our function. Now we'll make the height of the function equal to 1. Okay, so that's height 1. Okay, so it's going to be 1 is the function f of t, and it's going to be e to the minus I in omega naught t by dt. Okay, so when we integrate that, we get minus 1 upon I in omega naught. There's not a t in it, it's just omega naught. Okay, omega naught e to the minus I in omega naught t, and the limits from there for the integration are tau upon 2 to minus tau upon 2, and of course we've got our 1 upon t naught. Okay, so what we can do is we'll take the tau upon 2 in. Okay, so we're going to have 1 upon t naught. Okay, and it's going to be minus 1 upon I in omega naught e to the minus I in omega naught, and t gets replaced by tau upon 2, and it'll be minus, this negative again, so it'll be plus 1 upon I in omega naught e. Now it'll be minus tau, and the minus there will cancel out, so to give us a plus, so I'll end up I in omega naught tau upon 2. Okay, now what we'll do is we'll take out this I in omega outside the bracket, so you'll end up with 1 upon T naught I n omega naught. Okay, and inside the brackets, well, what we'll do is we'll write them round another way round about. So we'll take this one first and then this one next. So we'll have e to the I n omega naught top and 2 minus e to minus I n omega naught tau up and 2. Okay. Now what we can do is this looks awful like one of the trig identities we've seen, exponential identities we've seen earlier. So the sign identity is e to the I n omega minus e to minus I n omega upon 2i. Okay, so we could replace this by the sine omega, but we've got an extra 2i at the bottom, so what we'd have to do is we'll have to multiply by 2i, okay, in order to do that. So we'll just do that just now. So what we're going to have is we'll have 2 in the top, okay, and we'll have the I, which will cancel this I here, so you'll end up with T naught n omega naught, and in here you'll end up with your sine n omega tau by 2. Okay. Now another little thing that they do in order to get it in the right format is we multiply the top line by tau and 2 and the bottom line by tau and 2. Okay, so if you go through that, you'll end up with your final version of this: Cn equals tau upon T naught times sine a half n omega naught tau all upon a half n omega naught tau. Okay, so that's the final version, and I'll just put a wee box around that. That's what we're looking for. Now we knocked it into that shape there, so that whenever you draw it out, now if we want to draw out this here, I'll have our axis here. Now we'll give this axis the name n omega naught, okay, because it's only active at integer multiples of a fundamental frequency. So that's the integer multiple n, and that's a fundamental frequency omega naught. Now it turns out, per chance, that because this function up here is an even function, and it's a real even function, then whenever we find the Fourier series of the real even function, we end up with another real even function in this frequency domain. Okay, so the real even function, it looks like that, if that's okay. So this is the window of the function. Okay, it looks like that. Okay, and it goes on and on and on and on. But you know, remember that this n omega is only discrete values of frequency. So we've got a frequency component here, and say here, and I'll just throw in a few just so you can see. Okay, and the same in the negative side. Okay, so our function looks like this. Okay, and the height of the function there, again, that's the real axis. Okay, the height of the function there is it's tau upon T0, and it cuts the axis there every, it'll be 2n pi upon tau. Okay, right, now that's what we wanted to get. That there then is the frequency representation, the Fourier series representation of this time domain signal. Okay, now you'll notice that time domain signal, as I mentioned earlier, it is it's continuous. Okay, I'll just put in continuous. Continuous. It's continuous. It's periodic. It's running a wee bit slow, my machine today, I don't know why. And it's also an even function. I've got processes running in the background, I'm not sure what they are, but it's slowing it up a little bit. So our function here is continuous, periodic and even. So whenever we find the Fourier series representation of it, the Fourier series representation is, it's no longer continuous, it's discrete. Okay, it's discrete. Okay, and it's also an even function. Okay, so it's a discrete and it's an even function, and it's still periodic as well. Okay, periodic. Okay, so I'm going to go over another video and we'll go over even and oddness. Okay, because that there is an interesting, and it shows you can get a lot of information from the symmetry of these transforms. Okay, so what we'll do is we'll redraw this out again in another format so that we can get a better idea of what's happening. So let's say we put it in 3 dimensions like this, and we'll call that our n omega. Okay, and again it goes into the negative time as well, and that there is our real axis. Now we've got another axis there, which is our imaginary axis. Okay, and so this here is the complex plane, and it's extended out along the n omega axis. So again we can redraw this here, and we can see now that these individual lines here, okay, they're actually complex phasors. Okay, so in this instance, as I say, it just so happens that we end up with a purely real function. Okay, so it runs along just the plane of the real axis. I'll just kind of draw it in as best I can. Okay, now these phasors here, again, they're just running up like this. Okay, and running down like this. Okay, so now if we were to say, for example, we took this function we were approximating, which was the square wave. Okay, now if we shifted that square wave in time, okay, so now if we, instead of sitting there, let's say the square wave sat, say, over here, or maybe a wee bit further over here, or even further back the way. Okay, so we shift the square wave in time. Now whenever you shift the square wave in time, in effect what you're going to do is you're allowing these phasors to change their phase. Okay, so rather than this phasor, say, pointing straight up, that phasor might have pointed in this direction. Okay, and this phasor here might be pointing in this direction, and this one might be pointing in that direction. So all these phasors could be pointing in all different directions. Okay, so when we shift a function in time, okay, we shift the phase of the Fourier series representation of the function. Okay, Now, another useful way of looking at it, which I will get back to at some point, if we were to take the time axis, say, in this direction, so that's our time axis, that's the function of time that we want to approximate. Again, it's periodic, so there's a section here and also one up over here, okay? And that's the real number line, because it's just a real function of time. And we've just seen there now that we can find the frequency equivalent, okay? Now it's a discrete frequency equivalent, n omega naught, and we know it looks something like I'll just draw it out again there, okay? It looks like this, okay? Okay, we'll come back up. Okay, so now what we have is we've got a time axis here, and we've got a frequency axis there, and we can get an idea of a graphical representation of the Fourier series. If we think about this here as some surface, okay, now in this instance here, because it's an even function, all of this surface here will be a cos omega t surface, so that would be your omega, which would be one of your variables, and that would be the t, which would be another variable. And now, because it's purely even, this surface here would be a cos omega t. Now, if it was a purely odd function, then the surface here would be a sine omega t. Okay. Now, if it's neither an even nor an odd, then the surface here you wouldn't be able to draw, okay, because it would be a sine omega t and a cosine omega t surface, okay, because the surface would represent all the possible positions of your complex exponentials, okay. So, but we'll draw it out here now just to get an idea. We know that that's a real valued function and it's even. So what we're going to have is our little phases, and I'll just draw them like this, okay. So we'll have a 1 or 2, and there's a few here, okay. Now we can then go in here and say, well, in the center one here, the center one will be a single value, okay, and it will be a fixed value, so like in effect like a DC value, say in electrical engineering, okay. So that will have a certain value. Now the one further up will be a cos omega t, okay, so we'll have some sort of cos omega t, cos omega function, okay, so it's actually cos t, okay, and the next one up will be another cosine function which will just have a higher frequency content, and further up here as well we'll have higher frequency contents, okay. And then down this direction here you have your cosine values, okay, and as it moves further up this axis these will be at much higher frequency, okay. So imagine that's a high frequency cos. So then you can see that we have a real even function which is continuous, okay, and that real even function is continuous maps into a function which is still real and it's still even, okay, but it's a discontinuous, it's a discrete function, okay, because you're only picking out certain frequencies here, okay, so these are integer multiples of some fundamental frequency, okay, and you can see that you're integrating or adding them up along this direction here, okay, and you're getting your height here, okay. So that gives an indication of a way of looking at this, and you can think about this then I suppose as you could think of it as, and although you wouldn't really hear it described like this, but it would be a discrete frequency transform, because frequency is in this sense discrete. Now you can see that when we move on further on in signal processing, we can still work with a surface, but we could potentially have it the other way. We could have it as a discrete time surface, okay, and you'd have a discrete time, okay, Fourier series, and then you could also have it discrete in time and frequency, okay, and or else you could have it the other way around as well. You could have it continuous in both time and in frequency, and we would have a continuous function here. We give a continuous function here as well. So that's what we're going to be moving on to whenever we look at the Fourier series and other forms, okay, of the transforms. Okay, so I think that's all I want to talk about just now in this video. I don't think there's anything else I want to mention. Well, one other thing is that the reason why we went over this particular example is that we can use this example as a lead-in to deriving the Fourier series. Okay, so I think that's what I'll do next video. I'll go in and I'll use this to derive the Fourier series. Okay, thank you for listening. Goodbye.